So this tutorial is going to pick up on a discussion we were having about electric field lines. We previously in class discussed what a field line designates, what the rules are for drawing a field line around, let's say, a simple positive charge or a negative charge. Now we're going to look into more complicated situations. So we're going to look at three situations, with the last one probably being the most important. So let's jump right into it. I'll tell you what to draw and what not to draw, because I'm going to add a few extra things just for illustrative purpose. All right, so we want to be able to do for combinations of charges. So the most common combination is what is called an electric dipole. Okay, di meaning two, pole meaning we have two poles, like two charges. So in this case, we have two positive and negative in the vicinity of one another. And what our field lines are going to look like is the combination of each field line due to each charge. So again, don't draw anything at this point. Let's take, for example, a positive and negative. Let's choose a point in the field. The easiest place to start is somewhere between them. So if I start right there, the positive is going to want to push. Remember, we're testing with a positive test charge. The positive test charge is going to be pushed this way, and the negative is going to want to pull it this way. So the net result is going to be a rightward force. And no matter where we are along this axis, we are going to always be pushed or pulled to the right. The net force will be that way. So the arrow indicating the field line will be straight across, very simply. And notice that that arrow is showing that the positive and negative are connected. That would be indicative of attraction, which we'd expect between a positive and negative. Now, what if, say, we move off this axis but are halfway between? Again, don't draw anything just yet. So the positive would take our positive test charge, push it that way. The negative would pull it that way with an equal force, because it's equidistance. And if you recognize your vector addition, those two, the vertical components will cancel out, giving us a net force to the right. However, if I were to choose a spot, let's say, closer to the negative, then the positive would still push it, but since it's fairly far away with a weak force, the negative is much closer, it would pull it in with a large force. So the net result, and again I probably over-exaggerated, I drew the blue one too long, would be something like this, something down and to the right. Okay, now, so what's the upshot of it? If I were to keep following along that line of reasoning, the field line would look something like that. Okay, it would bow around this line, and it would do the same thing around here, connecting the positive and negative. Now, this is consistent with what I was talking about earlier, because if I choose a spot right there, the force at that point, based on the field line, is tangent to that. So that's exactly what we saw earlier, and if I'm right here, we'd expect something like that, which is kind of what I drew earlier when we had those vector sums. All right, so to complete this field, we're going to get the similar shape as we move further and further along this bisector, but since it gets further away, it's going to get weaker, so we're going to draw our much further apart lines. Okay, because we indicate weakness with further apart lines, more spaced apart. And then the only other part that we need to fill in are along here. Again, don't draw this, it's just a reference point. Okay, so it would make sense that anything to the left of the positive is going to be pushed to the left, stronger than it's going to be pulled to the right. So the net force is to the right, away from the positive, and it would come in towards the negative. And if we look at this field, we see that the field lines are always going away from the positive and always terminating at the negative. That's a really important thing to remember. So what if we had two positives? It'd still be a dipole, but a different one. Well, if we start in the middle, we can understand that the positive is going to push our test charge to the right, and this positive is going to push it to the left, and would cancel out. So we'd expect there to be no field there. So in the general vicinity, halfway between there, we expect to be a weak field or fairly far apart. If I move to a space right here, this one is going to push this way fairly strongly, this one is going to push this way fairly weakly, but we see that the net result is kind of like, it's going to be a field line that's fairly large, because there's a lot of vertical to that and not a whole lot of horizontal in that direction. So long story short, I'm not going to develop the whole thing. What we're going to get, and again, we should see our field line should show repulsion, is that we're going to start off like this and then kind of diverge along an invisible bisector. Okay, so in the area between them, there's not many lines because they're almost canceling out. And then off to the side, they push away from each other. They never cross. That's important. and then they would go out here and out here. So notice that our field lines are always emanating from the positive, going away from it, out to infinity in this case. Okay? So we would get something like that to complete it. And if we had two negatives, which I'm not going to draw here, look identical to this, showing repulsion. The field lines are pushing up against each other, but the arrows would be turned inward. Okay, so that's 5 situations looked at. 4 that we've drawn and 1 we can imagine. So an important question comes up. Are the fields shown in these 5 examples uniform in magnitude and direction? Uniform meaning the same throughout. Well, look at the ones that we've drawn before. Let's go back to one previous, right? You might say, well, this is symmetric about the positive. Is it uniform? And the answer is no, for the very simple reason that depending where you are, the direction is very different. And if I'm here versus here, the second hash mark I put there is much weaker than the first one. So even again, there's a symmetry there. It's not uniform. It changes in magnitude and direction. And the ones we saw here, we're definitely getting weaker the further we go, and the direction is always changing. So that's important is no. None of these fields we've drawn show a nice uniform field. So that's a very desired situation we'd like. So how does one get a uniform electric field where no matter where you are, you feel the same magnitude in the same direction? All right, well, there's a picture right in front of you. You can kind of guess, but this is extremely important. We will use throughout the year. You get a uniform electric field when you're between charged parallel plates. So imagine 2 small pieces of rectangular metal separated by a very small distance. It could be millimeters, it could be less than that, and we charge them up. So in this particular example, my top plate is positively charged, my bottom plate is negatively charged. So if it's a uniform field, we should anticipate what the field lines look like. It means the direction is the same no matter where we are. So how would I draw field lines indicating always the same direction? That's correct. They would be parallel. If I want to indicate uniformity, how would they be spaced? Correct, they would be evenly spaced. We wouldn't have one set closer than another. And in what direction would those parallel, evenly spaced lines be? Well, like anything else, always pointing from the, that's correct, positive to the negative. So I'm going to arbitrarily draw a number of lines here. I'm going to start in the middle. So I'm going to draw a line downward to the plate. It starts at one plate, ends at the other, doesn't go through it. I'm going to draw another one here, a third one, and then I'm going to do symmetry on the other side. And it turns out, even though we're not going to emphasize this, on the edges, things get a little bit complicated and they bow out. But for the most part, we're going to ignore the edge effect. When we talk about uniform field, we're going to be interested in somewhat on the interior. Okay, so let's look at what we can understand about that. So 2 electrons are placed between the plates as shown, E1 and E2. All right, which particle feels the greater force? Okay, so the whole point of an electric field is to exert a force on an external charge. So we're going to place electrons in there, and they're going to be forced one way or the other. But which of these 2 is greater? The tendency is to say, well, this guy might feel the greater force because it's closer to one of the plates. But that's not true. Remember, we're talking about a uniform field, so they feel the same force. They must. Everywhere in there is the same field intensity. So a given particle, in this case an electron, excuse me, is going to feel the same force. All right, if electron 2 is moved towards the bottom of the plate, so let's say I move this down to here, how would the force change? If this was between 2 parallel or 2 point charges, it would definitely change. But in this case, it's got to again stay the same because by definition, we have a uniform field. So no matter where you are, you feel the same force. Okay, for the electrons, how does the direction of force compare to the direction of the electric field lines? This is a little bit trickier. So the field lines are drawn based on a positive test charge. That's always our default. But in this particular field, we decided to put into it a negative test charge to actually see what happens. So now we just conceptualize that. A negative is going to be attracted to the positive plate and going to be repelled by the negative plate. So let me just redraw these. So in that situation, this guy is going to be forced upward. So I'll draw that I'm going to draw an arrow for the force. And next to the blue, I might label that E for the field intensity, which we'll define in the next tutorial. Okay, so you got to be careful to distinguish between the difference between force, which is what a external charge feels due to a field, and the field itself, which is due to the, if you will, internal charges, the things that caused it. Okay, so this is up. So an important thing to remember is that in a negative charge, force is always opposite direction of field. For a positive charge placed in a field, the direction of the force and field are always going to be the same. All right, if a proton were placed in the field, would any of the above change? So let's take a big old positive, let's put it somewhere here. Would anything change versus a negative? In one sense, yes. In another sense, no. Okay, what would be the same? Well, the force would be the same in terms of magnitude. In fact, I'm going to put an absolute value here for magnitude. Why? Because the charge of a proton is the same magnitude as a charge of an electron. So we'll learn that if you place the same amount of charge in a given field, it's got to feel the same force. What's going to be different? Well, I think you figured out because of the positive, it's going to be forced down. So the direction is opposite. How about the acceleration? Well, if the force is the same magnitude-wise, is the acceleration going to be the same magnitude-wise? And the answer is no, because they're not the same masses. Remember, acceleration depends on inertia. Proton has a lot more inertia, so it would have a lot less acceleration. That's something you want to be aware of. All right, the last question. How quickly is information about changes in electric field communicated? Okay, what am I talking about? So let's say I have a field charge right here that's positive, and a little charge is sitting there sensing that field. And let's say this charge is moved from one spot to another. So the field is going to change for this guy. Since this field charge moved, the field lines are going to shift. Well, how long before this guy feels that shift? Well, it can't be instantaneously. Nothing happens in physics instantaneously. It takes some time for that change, like a ripple in the field, to propagate. And that speed turns out to be none other than the speed of light. And that's not a coincidence. That's one of the most profound discoveries we ever made, and that's something we'll talk about at a later time. Okay, so that sums up the rest of the force fields.